2, ready, go.
Alright, so now I'll be doing chapter 18, problem 13. The problem reads 2-point charges are fixed on the y-axis. A negative point charge Q1 equals negative 25 microcoulombs at y1 equals plus 1.22 meters. And a positive point charge Q2 at y2 equals plus 0.34 meters. Our third point charge Q equals plus 8.4 microcoulombs is fixed at the origin. The net electrostatic force exerted on the charge Q by the other two charges has a magnitude of 27 newtons and points in the positive y direction. Determine the magnitude of Q2.
Okay, so let's put that in your own words. Okay.
Alright, so basically we have Q1 and Q2 both working, exerting a force on the point charge Q. And essentially what's happening is we're trying to determine the magnitude of Q2 based upon the amount of force that each charge Q1 and Q2 exerts on Q naught.
Right, and Q naught is, what is it, positive or negative?
Q naught is positive.
And Q1
and
is?
Q1 is negative. So these two are going to repel, whereas, no, they're going to attract. Right, these two are going to, Q1 and Q naught are going to attract, whereas Q2, we can assume is positive just because
they told us.
Oh. They did tell us.
Yep. Yep.
We can assume it's positive because they told us it's positive, so they're going to repel. So first thing I did.
So we're finding the net force and then going from there. Yep.
So the first thing I did was solve for the force between the two charges that we actually know the value of, Q naught and Q1. I just used Coulomb's law, which, just used Coulomb's law and plugged in my variables, and I found that the force between Q1 and Q naught was 39 newtons. And based upon the problem, they tell us that the difference, that the net force in the system is positive 27 newtons. So we know that, upward, sorry. Positive 27 newtons in the plus y direction. So we know that the value of the force of Q2, between Q2 and Q naught, has to be 12 newtons. Simply because the forces are going in opposite directions, and we know, not only now we know the value of the force between Q1 and Q naught, and we know the difference between the two forces in general. So we can use this equation, you subtract the 27 newtons, that is the difference in the magnitude, from the force that we found for Q1 and Q naught, which was 39 newtons, and we now know the force between Q naught and Q2 to be 12 newtons. After that, I used Coulomb's law again, set up the equation, and simply solved for Q2, where you would just essentially get 12 newtons, which we saw here, times the area, times the distance between them squared, over Q naught, and to give you the value of Q2 and K, actually. K Q naught, which will give you the value of Q2, which I found to be 1.84 times 10 to the negative 5 coulombs.
Yeah, and basically another way of saying it is that Q1 is negative, Q naught is positive, so they're going to attract each other. Q2 is positive, Q naught is also positive, so they're going to repel each other. You're finding the net force on them. Q1's force on the Q naught, and this is Q2's force on Q naught. Q2 is working in the opposite direction of Q1, but their net force is 27, and then you can just use that to back calculate the charge. And so that's very good. Thank you, Mr. Jarrett.